Hey there, chemistry team. This is your chemistry coach coming at you again with video number 6 in your coordination compound complex ion series. Although the first 5 videos covering, the nomenclature, introduction, and the chemistry, the equilibrium chemistry of complex ions, that's the first 5 videos. That's all that's going to be fair game on quizzes and tests and labs and stuff like that. So starting with this video on, this is all fluff and stuff. This is fun. This is usually material I don't get a chance to cover in a regular semester because we just run out of time, and it's not critical for us to know to be able to finish our lab work. So I'm going to make video 6 and on, or the chapter 24 for us, part 2 homework, and all the videos involved with that. Extra credit if while you're stuck in your self-isolation in your home and you have some extra time because you're not commuting around and doing all that fun stuff and even going to classes right now. If you want to learn some extra material, just because you're interested, or maybe you're just desperate for extra credit. It's not going to be a lot. It's only 5 points. Probably not going to make or break your grade. But hopefully you'll just be interested in learning. And to me, this is the funnest part of complex ions. The beautiful, beautiful colors that they form. So this is going to, the colors that they form, which are fascinating, is covered by what's called crystal field theory. It's actually ligand field theory, which is a little more comprehensive. Crystal field theory just looks at the electrostatic part of it, which I think is a more simpler concept. So we're just going to look at part of ligand field theory, the part called crystal field theory. And that's going to help us explain these amazing colors when we do this lab. It's so gorgeous. Our equilibrium reactions lab. And it also looks at some of the magnetism. It has fascinating magnetism that comes forth from the process of these d orbitals. When the ligands come in and go towards those d orbitals, the crystal field theory focuses on that interaction between the ligands. Either that ligand's an anion or it's a polar molecule with that lone pair coming to dock in to form a coordinate covalent bond. That's an electrostatic process that crystal field theory looks at. It says, hey, these electrons in these d orbitals and that anion or that polar ligand coming in are going to be a little bit repulsive there. And we're going to take a look at how those repulsive forces cause the d orbitals. So I want you to pause this video in a second and review your d orbitals from first semester general chemistry, the 5 different. Remember, you get 5 m sub l values. You're right, -2, -1, 0, +1, +2. You get the dxy, dz, xz, dyz, dz squared, dx squared minus y squared. Okay! Remember, they look like the 4-leaf clovers except for the p orbital with the lobe around it and all these crazy things. So go look up the shapes of those d orbitals that resulted from quantum mechanics. It was in the quantum mechanics chapter we looked at for our first semester general chemistry, which I think was chapter 8. So take a picture of, have a picture of that with you. I'll draw them up on the board, and we're going to look at how these d orbital energies shift when the ligands come in. It's going to come in a certain way where some d orbitals shift up in energy, some shift down in energy, which creates fascinating concepts with magnetism and colors. Because again, color is just a photon coming in, causing an electron to get excited, and what makes these colorful is when it gets excited from a lower energy d orbital to a higher energy d orbital, those energies fall into the wavelength range of the visible region. And so you get these just gorgeous blues and reds and violets and yellows. It's so awesome. You'll see them in lab. So check out those d orbitals. I'm going to attempt to write them up on this board. All right, gang. So to get to the bottom of this, we're going to look again at the d orbitals, and I'll draw those on the next board, but there's 5 d orbitals. That's going to be set regardless of what species complex ion we're looking at. Doesn't matter. Those are going to be set. What will happen is the way the ligands come in and the number of ligands coming in will cause those d orbitals to shift in energies. We're going to want to be able to predict that because that will help us predict the colors and the magnetism. So this depends. Remember, there was a bunch of different coordination numbers, coordination 2, 3, 4. So we're only going to look at coordination numbers of 4 and 6, by far the most common ones. And if we had a coordination number of 6, that created an octahedral shape, right? So you got the 2 in the z-axis coming on the x-axis, 2 in on the y-axis. So they're coming directly, those ligands are coming directly on those all the axes coming in. Tetrahedral would be a coordination number 4, which is by far the most common geometry. And where you get the 109.5 degree bond angles. That's going to be a little harder to see when we look at how the ligands come in on those d orbitals for a tetrahedral shape. I'll do my best to draw that in 3 dimensions. Square planar, of course, is flat. That's special for coordination numbers of 4 with the nickel and cobalt triad. So those are kind of, sort of exceptions to the tetrahedral rule. And again, that's flat with 90 degree bond angles where the ligands are coming in directly on the axis. So if you're in the XY plane, they're coming in on the X and Y axes when you do that. So if you remember the octahedral, tetrahedral, and square planar shapes, 90 degree bond angles, 109.5 degree bond angles, 90 degree bond angles. So what I'm going to do on the next board is put all 5 d orbitals on there, and we have to look at each one of these in turn because it's going to our result will be different on the repulsive energies between the ligands and the d orbital electrons if it's octahedral, tetrahedral, or square planar, the splitting of the d orbitals, which is what crystal field theory is the splitting of the d orbitals when those ligands come in and repulse with the d orbital electrons. So let me draw those 5 d orbitals. Hopefully you got those, and we will be rocking and rolling. Woohoo! All right, this is going to bring back some bad memories. Remember quantum mechanics again. 5 values for m sub l, right? That gives us the 5 different shapes from quantum mechanics. All right, 4 of them have 4 lobes. The other one looks like a 2-lobe p orbital with a donut around the middle. Remember those? All right, let's take a look. I separated the 3 on top and the 2 on the bottom because of the way they're oriented. The 3 on top are oriented in between axes. The 2 on the bottom are oriented on an axis. That's going to make a huge difference when those ligands come in to cause d orbital repulsion and shifting of those energies. These tend to go in groups. So notice we got the dxy, the dxz, and the dyz d orbitals. What that means for the dxy is those 4 lobes are on the xy axis, plane, the xy plane, but in between the axes. See that? So the lobes are pointing in between the axes, not directly on the axes, but it's in the xy plane. Exact same thing for the dxz d orbital. It's in the xz plane, and the lobes point in between the axes. So they look the same. All I did is I switched the axes. So there's the z-axis, y-axis, x-axis. So you can see this is in the xz plane. This one's in the xy plane, in between the axes. The dyz orbital is in the yz plane, pointing in between the axes. So that's why I put the yz plane here and the x-axis pointing. So all I did is shift the axes so they all look the same. The point is the lobes point in between the axes in a specific plane, whether it's the xy, xz, or yz plane. Down here, the dx squared minus y squared point is in the xy plane, so it's just like the dxy orbital, but the lobes go along the axis. So there's lobes, 2 lobes pointing along the x-axis and 2 lobes pointing along the y-axis directly on there. So these 2 are going to have definitely different interactions with ligands when those ligands come in, because the ligands are going to come in, depending on the shape, along the axes sometimes, or in between the axes sometimes, depending if it's octahedral, tetrahedral, or square planar. The dz squared orbital has 2 lobes pointing on the z-axis with the little donut. We're not worried about that donut, we're worried about those lobes, right? So if ligands come in along the z-axis, that's going to be really repulsive. If they come in along the sides here, that's less repulsive. For these, if ligands come in along the axis, it's less repulsive, right? Because they're in between, and more repulsive for here because it's on the axis. Oh, so let's first, I'm going to leave these up there, and let's look at octahedral first. And I'm going to draw the ligands. So I'm going to pause this, draw the ligands up there, and then you can help me predict which of these d orbitals are going to shift to higher energies because of more repulsion from the ligands coming in versus lower energy. But by themselves, they're all degenerate. They're all exactly the same energy, right? Because there's nothing to break that degeneracy down. But when the ligands come in, that degeneracy can break down, right? Degenerate just means same energy. So remember that. In the free metal or metal ion, those d orbitals are all 5 of those are exactly the same energy, right? So electrons don't care which ones they go in, as long as if there's no electron in there, it'll go in there. If it's got an electron in there, it would rather stay separate, Hund's rule. And if they all have electrons, then they start pairing up. That scenario. So let me draw some ligands in here for an octahedral geometry. You ready for some more craziness? Trying to do 3 dimensions on a 2-dimensional board. All right, we got our 5D orbitals, but now these little black circles here, think of them as little spheres. We'll just assume this is an anion, a ligand that's an anion. So these are your ligands. If this is octahedral, they're going to be coming in along the X, Y, and Z axes, right? With 90-degree bond angles, along the axes. So if the ligands are coming along the axes, think about the repulsion energies, right? The dx squared minus y squared and the dz squared have the d orbitals pointing along the axes. So there's a head-on collision, boom, with those ligands coming in. Oh, repulsion, repulsion. You have increased electron repulsion, right? So we'll have more electron. Let's write that over here. Repulsion, which is an increased energy. Right, so the dz squared and the dx squared minus y squared, the d orbitals with the orbitals pointing along the axes for an octahedral shape, the ligands coming along the axes, boom, head-on collision. You're going to have more electron repulsion, so these end up going up higher in energy because of the increased repulsions. Whereas the dxy, dxz, and dyz, those orbitals are pointing in between the axes, and the ligands are kind of coming in between, like that, rather than head-on. Right? This is what the dx squared y squared is. This is where the dxy coming in like that, right? Through the sides. So there's less repulsion energy for these three. So we'll do less electron repulsion. So reduced energy. So these three with lobes along in between the axes, lower in energy versus the two lobes, the two d orbitals with lobes along the axes. You get a split between these two. These go higher, those go lower, and so the originally degenerate 5d orbitals now split. All right, let me draw that on the next board for you, show what that looks like. All right, you ready for the result of these ligands approaching in an octahedral shape? So again, this is the octahedral complex, d orbital splitting. This is what the octahedron looks like, and the ligands are coming in along the x, y, and z axes. So imagine this is the free metal ion with the 5 degenerate d orbitals, right? We don't have to write the labels of them because they're all degenerate. When the ligands come in, there's a mutual increasing in energy because they're all feeling some repulsion, whether they're along the axis or in between. So they all shift up in energy. So let's say this is the average energy of those d orbitals after the ligands have docked into place, right? And now we take a look at the splitting that happens because remember, the dz squared and dxy squared, which have lobes pointing along the axes, repulse more. So their energies split to a higher energy. And the dxy, dxz, and dyz with the orbitals going in between the axes, lower in energy versus the dz squared, dxy squared, minus y squared. That creates a splitting. We call that the crystal field splitting, right? That's why it's called crystal field theory. We give that a large triangle with a sub O, the delta, the change in energy due to the split for an octahedral complex. We're going to do that for tetrahedral and square planar as well. And then we'll go to other videos to look at how that affects magnetism, and then another video on how that affects color. So let's do the exact same thing for a tetrahedral complex, which is totally different because the ligands come in not along the axes. It's a little bit different. So the splitting turns out to be the opposite. So write that baby down. That's called crystal field splitting. And the size of that, the size of that crystal field splitting is going to have a huge impact on whether on the magnetism of these species, whether paramagnetic or diamagnetic, as well as the colors, the wavelength of photons they absorb coming in and the colors that result of that. Really cool stuff. You ready for tetrahedral splitting? Oh, this is one of the harder ones for me trying to visualize this, although most people say square planar is the hardest. All right, so we got tetrahedral complex. What's the d orbital splitting? So in this case, I kind of drew a tetrahedron a little different than I would normally draw it. So here's a cube. In red, imagine the center is the metal ion, right? And then you've got the ligands coming in, and then you've got the z, x, and y axes. So it looks like 3 of those are sort of coming in between the axes, and 1 of them sort of coming in along the axes, so it's not quite as distinct. Octahedral, they all come along the axes, all 8 of them, right? So for this one, the 4 that come in are mostly in between the axes with 1 sort of. So the splitting's not as great. So the octahedral splitting might be this much. The tetrahedral splitting might be this much. That's going to have some big consequences. I'll show the energy differences in the splitting in the next board. I just want you to get an idea of why they split. So since most of these ligands are coming in between the axes, the dxy, the dxz, and the dyz tend to repulse more because the ligands are coming in along in between the axes. So they shift to a higher energy, whereas the dz squared, dx squared minus y squared with lobes along the axes shift to a lower energy. It's exactly flipped from what the octahedral one was. And so that crystal field splitting has the delta symbol, the change in the energy, sub T for tetrahedral. And we're going to find that that's smaller. So if that's the tetrahedral one, that might be the octahedral one. Octahedral, tetrahedral. And I'll put specific numbers on that. So a little bit harder to see, I think, than the octahedral one. So let's do square planar, and then we'll look at the energies, and that will be the end of this video number 1. Says Deadpool. Oh man, square planar. Most people think this is the hardest splitting to do. Square planar complex d-orbital splitting. Good thing we're only doing octahedral, tetrahedral, and square planar. And good thing not too many, just the nickel and cobalt triads are doing the square planar with a coordination number of 4. So again, let's draw the z, x, and y axes. And remember, square planar is flat. Right? So these ligands represented by these red dots are going to be coming along the x-axis and along the y-axis. Right? Ooh, coming right at you, or right in my face. And so the increased repulsions happen along the x and y axes and in the xy plane. Anything in the z plane, there's less repulsion. So let's take a look at the different d orbitals. Remember, there's a couple d orbitals that are in that xy plane. The dx squared minus y squared is in the xy plane along the axes. So that's taking the biggest hit. And the dxy is in the xy plane, but in between the axes. So the dx squared minus y squared has massive repulsion. I mean, head-on collision, just like in an octahedral scenario. So boom, that dx squared minus y squared just skyrockets in energy. The dxy shoots up as well, but not as much because the dxy, the orbitals are pointed in between the axes and the ligands coming through along the axes. But there's still repulsion because it's in the same plane. So those two shift up. The dz squared, that's a totally different axes, right? And the dxz, dyz, they all involve the z, so there's less repulsion, so they drop lower than the average. This would be the average of those d-orbital energies. So they drop a little more. But the dz squared is feeling a little bit more repulsion than the dxz, yz, but the differences between here and here are really tiny, really, really tiny. The overall splitting between the dx squared minus y squared all the way down to the dxz, dyz, that huge thing, that is the crystal field splitting for SP or square planar. We're going to see that's quite a bit bigger than the octahedron. But we're not concerned about that value. Notice this little one in blue. The textbook doesn't do this, but I put the triangle delta with a prime symbol. That's the one we're going to be focused on, because that's a big enough change, a big enough split right there where that can impact magnetism and color in those kinds of scenarios. So we're going to have 2 different splittings. One that's the overall splitting for square planar, and one is the one that we're going to focus on, that little one in blue. Let's do one more page, and I will, one more page, one more board, and I'll show you side by side the octahedral, tetrahedral, and square planar, and as far as their energy gaps, which ones are bigger and which ones smaller, and that will make a difference in their colors and their magnetism as well. Read it and weep, my friends. You either love this or hate it. All right, guys, let's polish this crazy stuff off. Good review, I think, from these d orbitals. Hold on, let me shut the door my son left open, and the noises of my crazy house come filtering in. That's better. All right, here we go. So octahedral complexes, tetrahedral complexes, and square planar complexes. You'll see these 2 most often. that much less often because it's weirder. But hey, those nickel and cobalt triads, what can you do? All right, so here's our energy range. For an octahedral complex, you get the dz squared, dx squared minus y squared going up, dxy, dxz, dyz dropping because the lobes are in between the axes. These are along the axes with the crystal field splitting of the delta sign with the sub O for octahedral. Tetrahedral, you get the reversed, right? Because with the tetrahedral, there's more repulsion in between the axes than along the axes. So the dxy, dxz, dyz go up. The dz squared, dx squared minus y squared go down a little bit, but not nearly as much, right? Because in the tetrahedral, the d-orbitals, the ligands come in between the axes in most of them, but along the axes sort of on one, so it's not quite as distinct as the octahedral and square planar. So the splitting is only about 44% of the octahedral, so it's much lower. That's going to have a distinct impact on the magnetism of octahedral complexes versus tetrahedral complexes, and then the colors that they form. Okay, so the tetrahedral crystal field splitting is about 0.44 the value of the octahedral splitting, or about 44%. Square planar, that's more dramatic because there's really high repulsions in the xy plane. So the x squared minus y squared dxy shift up, way more for the dx squared minus y squared because it's along the axes, whereas dxy's in between the axes. So you get this huge jump up here, and then the dz squared and the xz and yz drop a little bit, more so for the xz, yz, less so for the dz squared. Not too much of a splitting between those, but if you look from the very bottom to the very top, the crystal field splitting overall for the square planar complex is much more than that for the octahedral complex. It's 1.74 times higher than the octahedral. So here's tetrahedral. Here's octahedral, there's square planar, all right? Tetrahedral, octahedral, square planar. Whoa! But again, for the square planar, we're commonly looking at the difference between the dxy and dx squared minus y squared, which is very close to the octahedral splitting, which is quite interesting. So a lot of times, I put the prime up there, which isn't critical. A lot of times you'll see some people put a sub O there, because it's very similar in value to the octahedral crystal field splitting. So we shall look in the next couple of videos. I'm going to do one about the different types of ligands. What determines the magnetism and the chemistry is, one, what kind of complex, octahedral, square planar, or tetrahedral. Two, what kind of splitting occurs, right, based on that complex because of the way the ligands come in. Three, what'll make a big difference is the type of ligand. So some ligands cause more repulsion, some ligands cause less repulsion. We call them strong field versus weak field ligands. So we'll do what's called the spectrochemical series on the next video, and then we will look at the impact on magnetism and the impact on colors after that. Enjoy your extra credit videos, my friends.